Good morning, everyone, or good afternoon. So a little bit of a different kind of talk. This is going to be an academic talk. I don't have a product to sell. I don't have hardware anyone can use. I don't have much of anything people can use. I'm interested in conceptual advances that make it out to the real world in a few years. And let me start with a slide from 20 years ago. Ed So is a professor at Cornell now. He's a full professor at Cornell. And here's a slide from his talk at the International Conference on Supercomputing. And we didn't call these things enclaves, but we talked about attestation. We talked about minimizing trust, minimizing the trusted computing base, protecting, you see a secret key in there. Those keys are secret keys. and you can see that this slide is old, right? I mean, look at that CD-ROM there, right? I mean, a lot of old people here, so you remember CD-ROMs. But if there were students here, I have to tell them what it is, right? So anyway, happy to see enclaves, getting a little attention. Happy to see enclaves getting a little attention. So one thing that we have now, of course, is some level of deployment. Just wonderful to see Intel SGX come out, and then TrustZone was before that, AMD SCV soon after SGX, and really a host of academic and research lab efforts that you see here. That's the good news. There's some bad news. So I want to be careful because I don't want to get sued for defamation here. But if you look at the strongest threat models that include side channel attacks and privileged adversaries, you could argue that they're all broken, right? Mostly broken, all broken. And if you go to architecture conferences, there's sessions on breaks associated with these deployed architectures and academic architectures, and I've proposed some that have been broken. We're all in the same boat here. There's Spectre and there's Meltdown, and we had that wonderful talk from Signal, Rolf, talk about side channels and how insidious they can be. You'll see a whole bunch of papers, and I think the most difficult part of this would be if the attestation mechanism got broken, right? So you get a computer in a lab, and then you have complete access to it, and then you break the attestation mechanism, and then you can go attack things that are out in the real world, right? So we got to be careful about this. I'd love to see hardware vendors addressing this problem with greater focus. So maybe this is a little bit unfair. They're not addressing. And there are a lot of academic proposals, partly because it's easier to write software than build hardware. They're limited to software changes. A lot of the times, side channels are considered out of the threat model. I mean, the papers just say, well, these are out of our threat model, but that doesn't mean that you can't tell an attacker, well, you can't do that, right? It doesn't work that way, right? We're trying to fix this. So have a sequence of processors. This is, I guess, I kind of have lost track. But we had a processor called Sanctum back in 2016 that was based on the RISC-V that was side channel resistant. It was an in-order processor. And then Spectre and Meltdown came out, and we had this processor that Raluca very kindly referred to in her talk. That's because she likes me. Called MI6, which was a riff on James Bond and Spectre that was protecting against speculative execution attacks, and that had issues. It was basically completely unusable. And so this is, slightly less unusable, but I'm going to tell you about it. So Citadel is hardware software co-design. It tries to address, people would like to use this, and you want performance at the highest level of security. You want to do things like communicate with the external world. Some of the problems with enclave systems is they only work for batch-style computation. But if you want to do interaction, then and query and things like that, maybe you could consider that basically little batches of computation. but it's hard to run interesting programs if you're stuck with batch-style computation. And we'd love to essentially target the highest level of security, which is transient execution attacks, yada, 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 and all of those good things. So if you want to communicate with the external world, and this is kind of the one new thing in Citadel, you need secure shared memory. The operating system, which is untrusted, is using some memory and depositing something into memory, and you want to read from it as the enclave. How does that work? Is there a side channel there? Yeah, sure. How do you protect against that? And we'd like to build this. We're interested in conceptual advances, as I said, but we want to do prototypes. And sometimes you really can't explain to people, what your work is about and why it's interesting unless you go build it. So our work is built on Amazon F1 FPGAs. And so there is hardware and software. And so this processor is certainly, in that it has an implementation. And it's fully open source. So I'm just going to give you, in the 3 minutes I have left, an overview. There's a paper on archive that people are interested can look at. There's a GitHub site that I'm going to tell you about. And so happy to, John was talking about, Manfredelli was talking about open source. Well, here's another kind of shaky open source platform to add to the mix. And so the hardware is a RISC-V out-of-order multiprocessor, a multi-core processor that was built at MIT several years ago from Professor Arvind's group. It's called RISC-V ISA. It's like a graduate level course. It's got some fancy architectural features, scoreboarding and things like that. And it's well, we are doing the 2-core version, but you could do more. We had mechanisms to clean microarchitectural state. One of the nice things about clean slate design is that you can go look at side channels and you can clean them up. You can look at every microarchitectural register, every piece of memory, and you can say, I'm going to clean it up to make sure that it doesn't leak, right? And that's basically what we did. That's what we did in MI6. But as I said, it was something that was limited to batch computation, but we can certainly run with that. And then we wanted to add to that ways that we could actually use this. And so again, it was very simple programs. But now we're up to running secure crypto libraries and a MicroPython runtime. And we have an attestation mechanism built in, et cetera. And the key is 15,000 lines of trusted computing code, right? So you trust the hardware and you trust 15,000 lines, as opposed to 100 million lines, right? And we've looked at, from what we can tell, or we thought we did, looked at all of the side channels, right? And we missed one. And we missed one. Right, submitted a paper, and then realized that there was a side channel in here associated with the cache coherent memory. And the fact is that, if you're Daniel Genkin, who's and people who are really looking at this very carefully, they could probably find a way of, if they had this processor implementation in their possession, to exploit the side channel that's associated with differences in timing, associated with how fast cache coherent messages flow through the network. And so, that's a fix. So this is just a picture because I wanted a complicated picture. So hopefully you're all impressed, right? But one of the things that that you have to do right is, if you have a privileged adversary, you can't let the adversary have control over the enclave page tables. And the original version of SGX, and I'm not sure about the later ones, the operating system has control over the page tables. So one of the first things we did in our processors was have separate page tables associated with the enclave and the untrusted operating system. And so because of that, you have to be careful about speculation and not speculate when you're actually accessing shared memory. So we do that. But even on top of that, it turns out that you have to be careful with respect to the instruction timing associated with the attacker, where, because you have these cache coherence messages going at different times, you got to fix that somehow, right? So we have a fix for that. We built it into hardware. And I'm just telling you this because I'm telling you things are complicated. But if you do want the sort of pristine, secure processor where you can guarantee protection against all these side channels, this is the kind of thing you have to do. You can't just partition the L1, which would fix pretty much 90% of the problems, but there's 10% left. And as it turns out, kind of an easy fix, at least from our standpoint, is to do shared memory access through DMA, and then arbitrate requests at the L2 entrance. So now we think we have a processor that's secure against transient execution attacks. It's out there, for you guys to attack and play with, and so you can. I don't make any promises about whether it's going to run or not, but it's out there. Okay, and that's what it is. And thank you very much. So.